Hello, bonjour à tous. Je m'appelle John O'Reilly. J'habite dans l'ouest de l'Irlande et je travaille pour une compagnie norvégienne qui s'appelle NEAT. Et c'est un plaisir d'être ici à Paris aujourd'hui. Et maintenant, et peut-être malheureusement, anglais. Merci. I keep joking with Martin Bonin that someday I'll give a talk fully in French, but I think I'm about 15, 20 years away from that, maybe. So we'll see. So the plan today is that we're going on a guided tour of various libraries used in a number of the Kotlin multi-platform samples I've been working on, along with other folks, over the last 5 years or so. Just the usual show of hands. How many people here have used Kotlin multi-platform? OK, quite a bit. And Compose multi-platform? OK, a little less, still quite a few. As you can imagine, I've been asking this question in talks over the last 5 years, and it's been fantastic to see the steady increase in people using it. Just to start with a very tiny bit of background, I started taking an interest in Kotlin multi-platform around the end of 2018, and I had, at this point here, just about got something very basic up and running using the Galway bus project. This had just been an Android app at the time, and wasn't generally a project I was using to try out new technology. Interestingly enough, the following day, June the 3rd, 2019, SwiftUI was announced at WWDC and was available to try out straight away, which of course I did. Jetpack Navigation had been announced at Google I/O a few weeks before that, and so began this amazing union of declarative UI and Kotlin multi-platform. And 5 years later, this is where I find myself, with 11 KMP samples now, a number of them created in collaboration with other folks. I'm determined, by the way, to try to put a pause on creating any new samples, at least for a short while. So these samples cover use of a range of architectures, remote access, persistence approaches, and different libraries used for each in some cases. Not going through all of them, but we'll use a number of the samples to illustrate various patterns and some examples of how these libraries are used. By the way, I'm including links in various places so that hopefully these slides can act as somewhat of a reference for folks that want to look into them in more detail at a later point. And we're going to focus in on these 5 specific samples as a basis for our exploration, illustrating use of the KMP and CMP libraries shown. These cover different approaches for retrieving data from a backend, persisting locally, dependency injection, view model component sharing, Swift Kotlin interop, packaging, and even making Gemini AI requests, and also include a number of Compose multi-platform UI libraries as well. There's quite a few libraries here, so obviously we won't be going into great detail on each one, but hopefully we'll provide at least a flavor of what the library does and how it can be used. Before we go into details, I just want to give a big shout out to all the folks who've contributed to those samples over the years. In a number of cases, this was their first contribution to open source. And thanks, by the way, to Stilian Elskakis for the Kotlin script to query GitHub to get this information, which I then, of course, felt compelled to put a small Compose for desktop app around, as you do. And great to see some folks on this slide in the audience here today. By the way, these are the full set of libraries used in the samples. We have a number of the standard JetBrains libraries, a couple of libraries from Google that now support KMP, and then various third-party ones. Important to mention, of course, that there's a ton of other libraries available now as well. And speaking of which, just to highlight, as you might have seen in Martin's talk earlier, just how many more KMP libraries there are now. When I started looking into KMP in 2018, I think there was maybe a handful available at the time. And now, not only do we have third-party libraries, but likes of Google now porting many of their libraries to work with KMP as well, which is great to see. So the first of the 5 samples we're going to cover is people in space. This was the first dedicated Kotlin multi-platform sample I created. The functionality in it is quite minimal, shows the list of people in space and the position of the International Space Station. But it covers a wide range of platforms. We have Android, Wear OS, and iOS here, along with Compose for desktop and Wasm-based Compose for web clients. It also has a watchOS and a macOS clients as well, along with a Ktor-based backend. And this is a high-level architecture diagram showing the key moving parts of the project. By the way, the libraries shown on the right of these diagrams are the ones we're going to focus on and illustrate in each section. In this sample, we're using native view models, but in most of the others, they're shared. I wanted, in general, to ensure the samples collectively covered a range of different usage patterns. This project was initially intended to be as minimal as possible, so basically just repository and remote API classes in the shared KMP code. We're using Ktor to make remote HTTP requests to the backend, and SQLDelight then to store the data locally. And that database is what's used then to drive the UI. The combination of Ktor and SQLDelight is probably one of the most common used in building KMP applications. First library we're going to talk about is Koin. It's the dependency injection framework I use in most of the KMP samples I have, and one I've been using in work projects as well for several years. We define our dependencies in a series of Koin modules. In a KMP project, we typically have one module for common dependencies, as shown here, and then use expect actual for a platform module that we define for each platform, as we'll see shortly. And also showing here an example of injecting the people in space API dependency in the repository class. In this project, we're instantiating that repository class directly from Swift, so using Koin component, which allows us to inject dependencies using this approach shown here. In a project where a view model, for example, is shared, then the repository dependency would typically be injected into the constructor of the view model, and we wouldn't need to use Koin component for this class. And these are the platform modules for iOS and Android, for example, using for the SQLDelight database driver and the Ktor HTTP client engine, which need to be defined separately for each platform. And as we'll see shortly, these platform-specific versions of these dependencies will get injected in automatically to common code that depends on them. Next up, we're using Ktor for making remote HTTP API requests to the backend. Again, a very lightweight and easy-to-use framework. Ktor includes libraries for both client and server, but we'll be focusing on the client here. By the way, there are Ktor-based backends in a number of the samples if folks are interested in taking a look. And this is some of the plumbing to allow using Ktor. We're using Kotlin X serialization, so just need to configure that so it can be used, for example, for deserializing the JSON we get back into Kotlin data classes. That's passed to create HTTP client along with the client engine we showed earlier. Note again, this is common code, but then appropriate platform-specific versions of the engine will get injected here. Here we see again the Android and iOS specific version of the Ktor engine being created in Kotlin platform-specific modules. And finally, this is the code we use to make the queries along with the associated data classes. We have data classes for the list of people and also for the position of the International Space Station. And then two methods in the API class that use Ktor to make requests to the backend, with Kotlin X serialization being used under the hood to deserialize the JSON we get back into those data classes. And again, we use Koin here to inject the HTTP client object into the people in space API class. Okay, now that we've got our data from the backend, we need to store it locally on the device. And for that, we use the SQLDelight library. This works by generating type-safe Kotlin code from a series of SQL statements. And these are the SQL statements for the people in space sample. We have a statement for creating the table, and then ones for inserting, selecting, and deleting data. I note that the names shown above the statements are what we use in the Kotlin code, or what are used, in the Kotlin code generated, as we'll see next. We can now use that generated code to store the data we get back from our backend into a local database. We create here, for example, a transaction, and within that, we delete existing entries and store the new ones. Again, note that delete all and insert item were generated based on what we defined in our SQL file. And this is how we retrieve the data from the database and expose as a Kotlin flow, which we'll use to drive our UI. We also use this mapper here to convert the result of the query into a Kotlin data class, which we expose to the UI. And just a very small example from the project of a SQLDelight database migration as well. One other library I want to highlight for this sample is KMP-NativeCoroutines, and it's one I use in a number of the other samples as well. It supports mapping Kotlin coroutines to a range of different Swift concurrency frameworks, but these days I'm using it primarily for mapping to new structured concurrency capabilities introduced in Swift 5.5. Showing an example here from the people in space where we have a Kotlin method in shared code that returns a flow representing the position of the International Space Station. And then in Swift, we use for-await to observe the data. For-await being effectively equivalent to collect in Kotlin. And note that if this is cancelled in Swift, then that cancellation gets propagated to the Kotlin flow as well. We can also use KMP native coroutines to seamlessly invoke suspend functions using Swift's await. Next up is Confetti. This is a KMP project for showing information for a range of conferences, for example, Android makers. It includes various clients, along with a GraphQL backend, thanks to Martin Bonin. Here we have the iOS and Android clients, and also a Wear OS client, which was created by Yuri Shimka, who, by the way, has contributed Wear OS clients to a number of the other samples as well. It also has a Compose for desktop client, and also we're currently working on a Wasm-based Compose for Web 1 as well, as shown here. Again, showing the high-level architecture. key thing here is the use of Decompose components and using Apollo to interact with the GraphQL backend. We'll talk about both shortly. We're also sharing some of the Compose code across the clients, including on iOS. And showing examples in this section of the libraries shown on the right. As mentioned, the clients in the project interact with the GraphQL backend, and for that we're using the Apollo Kotlin library. It's described as a strongly typed caching client that automatically generates APIs from our GraphQL queries and backend schema. And that caching aspect is very important as well, giving us effectively an all-in-one solution, both for retrieving the data from a backend and storing it locally. So we need to create an Apollo client object to make various requests, and this is an example from Confetti of how that can be done. We provide, in this case, the URL, a header containing the conference name, and details of both the in-memory and persistence cache we'll be using. And showing a few examples of its usage. Firstly, for retrieving the list of conferences. At the top right is the query that this is based on, and below is the use of the Kotlin code that Apollo generated. The conference data class reference here is also generated by Apollo based on what we specified in the query. And then this is what's known as a GraphQL mutation, where we update data in the back end, in this case adding a bookmark for a session. And again, we make use of the Apollo-generated code to perform that mutation. Next up is Decompose. This is a library based on the idea of breaking your code into a tree of lifecycle components that contain observable state, have routing navigation functionality, and into which you can plug your UI. So this library is broader in scope than most of the others we're showing in the talk, and quite a few moving parts, but hopefully these will become clear in the following slides. I just wanted to do another quick show of hands out of curiosity. Is anybody here using Decompose? Okay, a few. So yeah, very interesting. Like I said, it's a library that is a little bit of a learning curve and takes a while to get up and running, but once you do it, it's extremely powerful. So these are most of the Decompose components used in the Confetti project. We see, for example, ones for the list of conferences, session info for a particular conference, speakers, bookmarks, venue, etc. And if we focus in, for example, on these particular components, these are the set of components associated with the screens we can navigate to from the home screen as shown here, corresponding to tabs at the bottom, sessions, speakers, bookmarks, and venue. And a key thing here is that the components themselves know nothing about the UI. We just hook up particular UI screens elements to the appropriate component. First thing to show here is a set of children defined for home component. We'll explore a little in the next few slides an example of how we'd navigate to speaker's child and associated UI. So if we drill into a somewhat condensed version of home component, this is the Decompose component, which, as we mentioned, is associated with the home screen in our app. First important concept here is the child stack. It's described as a navigation model for managing a stack of components. The UI, as we'll see shortly, will observe the current active child in the stack and use that to decide what to show. The child stack is also passed a factory that's used to create child components, which we'll show next. This is the child factory mentioned, and it's used, as the name suggests, to create particular children given configuration passed to it. For example, config.speakers maps to child.speakers, which in turn is used to wrap an instance of speakers component. So quite a few abstractions here, but as we see, it accommodates quite a large number of different use cases, which is quite powerful. We also see an example of how we'd navigate to that child in this on-speaker tab click method that's invoked from the UI. That navigation.bring to front is past that config.speakers configuration, which, as we saw, will map to child.speakers, which then becomes the active child. Okay, a lot to take in there. And this is the speakers child component associated with a list of speakers. We pass it the conference name and a callback for when a speaker is selected. That callback will then, in turn, trigger navigation to the speaker details child, passing in the associated ID. And this component basically acts quite like a traditional view model in that it will expose observable state to the UI. It will also provide actions we can invoke from the UI, such as the on-speaker click as shown here. And this is how we decide what to show in the UI, in this case in the Android Compose client. We observe that active child instance from the component stack we saw earlier, and navigate to the appropriate screen based on it, passing in, importantly, the associated child component as well. An almost identical code then in iOS SwiftUI client, for example. Again, observing the component stack to decide which view to show. Next up is the Multiplatform Settings library, designed to allow persisting key value data in KMP projects. So this is an excerpt from the Confetti project where we're storing the name of the conference a user selected. If that value was set, then we bypass that conference in the list screen the next time the app is launched. And we're also observing that setting as a Kotlin flow. By the way, that flow settings type of the settings parameter is abstraction from the Multiplatform Settings library. And we use platform-specific code then again to create the appropriate implementation of that. These are parts of the Koin platform module definitions for Android and iOS, for example, using data store settings as an implementation on Android, and NS user default settings on iOS. Okay, we can't really do anything these days without some mention of AI, so I'm going to show the use of the library as well to make Gemini AI-related queries in the Confetti project. The library used is based on a fork of the Android version and uses HTTP requests to allow it to work in a KMP project. I'm also going to make use of the build config KMP and markdown render CMP libraries as well in this example, as we'll show in the next few slides. In the mobile clients right now, the Gemini API requests are formed in such a way to allow us to correlate results with particular sessions and show associated info then in the results. We'll show details shortly about how that's done. For example, here we've requested, of course, to show AI-related talks at the conference. And this is taken from the class that wraps use of that library. We'll show next how we're creating the prompt that gets passed to that generated content. And using build config, by the way, to set the Gemini AI API key in this shared module Gradle build file. Very useful capability to have. And this is then how we're creating that prompt that we pass into the API. We firstly create CSV data from our list of sessions, including speakers, session ID, and title. That info then is included in the prompt along with the query we have entered in the UI. The results then are returned as a comma-delimited set of sessions, a session ID, which can then be correlated with our list of sessions and render those in the UI. I'm hoping I can call myself a prompt engineer after doing this, so maybe, let's see. And this example from the Decomposer desktop client, which allows more free-form entry of a query. The prompt in this case includes both the query that you can enter as shown here, and also the CSV version of the session info mentioned before. And we're using that markdown render CMP library I mentioned to display the results of the Gemini query. The last library I'm going to show for this project is Coil, the one that folks might be familiar with from Android. It provides image loading, rendering functionality, and also now supports Compose Multiplatform. And this is a small example of it being used to show profile image in the session details screen in Confetti. In this case, in shared Compose Multiplatform code that's also being consumed in the iOS client. Next KMP sample is bike share, a third of the 5 we'll be using. This shows the list of bike share networks for particular countries and bike availability info for each network. We have Android and iOS clients, and also Compose for desktop client, and as shown here, of course, a Wasm-based Compose for Web 1. Again, the high-level architecture diagram. In this case here, we're using KMMViewModel for our shared view model, using Ktor to retrieve the data from the back end, and then persisting it locally using the Realm Kotlin library. And we'll be talking in this section a little bit about KMMViewModel, and also a plugin for generating Swift packages from shared KMP code. So KMMViewModel is described simply as a library that allows you to share view models between Android and iOS. A key aspect of this is what it offers is ability to expose Kotlin state flows, for example, as Swift properties that can be directly observed in SwiftUI, as we'll see next. And this is an example of one of the shared view models in the bike share project, in this case exposing the list of countries that we're displaying. We're using our repository class to get the list of countries, augmenting that with some information, exposing then as a state flow. And this is how that's consumed in SwiftUI in the iOS client. We instantiate the view model we saw on the previous screen using @ScreenViewModel property wrapper provided by KMMViewModel, which then allows that country list state flow from the view model to be observable directly in a Swift, as a Swift property, which is pretty powerful. And this is the Android Compose equivalent. On Android, the standard Android X view model is used under the hood, and we observe the state flow as normal, using, for example, collect as state as shown here. As with the SwiftUI client, any change to country list then will cause the UI to be recomposed. Next up is a Gradle plugin that generates a Swift package from our generated code, which then can be easily added in Xcode. This is an example of the associated build config from the bike share project. Here we're targeting the iOS and macOS platforms. In this case, I've published the output of that plugin as a separate GitHub repository, but also could be done in the same repo. That repo, by the way, includes an example of SwiftUI code you can use then to consume the Swift package if people want to try it out. And a very small recording then of showing how to add the Swift package to an iOS project in Xcode. We create a new iOS project. We then copy the URL of the GitHub repository. And this repository contains the package, and then use that to add a package in Xcode. And lastly, we copy the example SwiftUI code from that repo README and paste that in, and we're ready to go. I wanted here to also show, in general, just how easy it is to consume a Swift package containing the shared KMP code like this. And most of what's shown here is the same regardless of how that package is created. And lastly, we see, hopefully, this, well, it's recorded, so it's definitely going to happen, of this exciting SwiftUI client that is from there. So a powerful capability, and really important. As I said, this, I think there's been an evolution towards the use of Swift packages, which I think has made this a lot more interesting. And by the way, another more recent and much more comprehensive approach you can use for creating such packages is KMMBridge, which I definitely recommend looking at. It takes care of both producing the package and publishing it, and also provides capabilities for local development. It's an approach we're actually starting to explore using in the Confetti project. Okay, we're getting there. The fourth of the 5 KMP samples we're covering is Fantasy Premier League. It shows information for a competition for the main football league in England. These are screenshots from the Android and iOS client, and this is the Decompose for desktop client. So similar to bike share, we're retrieving data using Ktor and storing locally using Realm. We're also using shared view models, but in this case, we're using the newly announced alpha version of the Jetpack ViewModel library that now supports Kotlin Multiplatform, as you might have seen Martin mention earlier. And using shared Compose UI code here as well. In this case here for the player details screen, as we'll see shortly. In this section, we're going to talk a little bit about use of the aforementioned Jetpack ViewModel, data store, Realm, SKIE, and this CMP library called KoalaPlot. So quite a few things. This is the announcement I mentioned about Jetpack ViewModel now supporting KMP. And it looks like we'll continue to see more previously Android-only Google libraries like this move in this direction, which is great to see. So this is an example from the project. It looks like a standard Android ViewModel that many of us have used in Android apps before. Difference here is that it's defined in shared common Kotlin multi-platform code, thanks to that recent alpha. There's an ongoing discussion right now, by the way, about how lifecycle of this will be managed by likes of Coin in a KMP environment, related as well to Jetpack Navigation now being available in KMP code as well. And you might have seen it as well from Martin's talk earlier about some of the lifecycle changes and the KMP-compatible lifecycle changes and view model owners changes that will kind of enable that as that's developed. Similar to ViewModel, Data Store is another Jetpack library that now supports KMP. It's been available in pre-release versions for a while, but went stable just last week. It supports storing key value information, as well as typed objects using protocol buffers. This sample had in fact been using the Multiplatform Settings library, but I recently migrated it to use Data Store directly. And this is an example of it being used to store the particular leagues you're interested in looking at. The data store object is injected into the constructor by Coin, with implementation again being created in platform-specific modules. And this is what we have in platform module for Android. And then for iOS. Specific detail is not too important, but just to show again how KMP's expect actual mechanism, in conjunction with Coin, allows us to easily plug in platform-specific code like this. Next library we want to talk about is Realmcin. As described in documentation, it makes persisting, querying, and syncing data as simple as working with objects in your data model. Okay, quite a mouthful. So quite different from approach of, say, SQLDelight, in that it supports working with objects directly, as we'll see next. This is an example from the project of a class representing a football fixture. used, for example, for displaying the information shown in the screen on the left on various platforms. And by subclassing Realm object like this, we're able to directly persist the object into the database. Note as well that this has references to TeamDB object, which is also persisted. And here's an example of code to iterate over the list of fixtures we got from the back end and write them to the database. And this is done using copy to Realm as shown here, and also showing how we can set those home team and away team properties to the associated DB object as well. An example of code then to read those fixtures from the database, returning a flow, which again we can use to drive our UI. The next library we're going to be using in this project is SKIE from Touch Labs. SKIE stands for Swift Kotlin Interop Enhancer and supports a range of functionality as mentioned here. And we'll show next how we're using some of these features in this project, specifically for the coroutines flow and sealed class support. First up, invoking Kotlin suspend functions from Swift. We have a getEventStatus suspend function in shared Kotlin code, and we're able to use Swift's await to invoke it then in our iOS client, thanks to SKIE. Likewise for flows, we have this player list UI state flow in our ViewModel. And we use Swift for await to observe that in our iOS client. That Swift for await, as mentioned before, is analogous to Kotlin's collect. And as with KMP Native Coroutines, when the SwiftUI screen that's used in is no longer shown, then it's automatically cancelled, and that cancellation is propagated to the Kotlin flow as well. Another area where there's a disconnect between Kotlin and Swift is sealed classes. And this is something SKIE also addresses. We have this player list UI state that's being emitted from our ViewModel, as we saw before. And SKIE then provides a way to exhaustively switch over the sealed class hierarchy by generating a Swift enum that wraps the Kotlin sealed class. And we can see, for example, in Xcode where it reports this switch must be exhaustive error if any of the cases are missing. As mentioned, we are sharing Compose code for the player details screen across the clients. That screen shows a graph, and we're using the KoalaPlot CMP library to show that. It supports a wide range of different chart types, but we're using it for this project for a standard bar chart, as we'll see next. And this is the somewhat condensed version of the code then to show that chart. Key thing again is that this is in shared Compose multi-platform code that is used for all the clients. And of course, I had to show at least one French player. The final sample we're going to use today is Climate Trace KMP, which shows per sector emission information for different countries. Again, we have an iOS and Android client, and also a Compose for desktop client and Wasm-based Compose for Web 1, as shown here. Again, showing the high-level architecture, using KMMViewModel, and using Ktor to connect to the back end. The plan is to update this project with local persistence functionality once such a library that supports Kotlin Wasm is available. For this sample, we're going to highlight the Voyager navigation library, window size class, and show example of consuming Compose UI on iOS, and a late addition yesterday, which Jetpack Navigation, which I forgot to mention in my notes. So first up, Voyager. This is primarily a navigation library that works across a range of Compose multi-platform clients. It supports a wide range of functionality, including different navigation types, state restoration, transitions, lifecycle callbacks, backpress handling, and deep link support, along with integration with a number of frameworks. It works on the basis of having your Compose code contained in these screen classes. This is an example from Climate Trace for the screen showing the list of countries. We see then use of Voyager's navigator.push when an entry is selected in that country list, causing us to navigate to country emissions screen, passing it the country object. And this is an excerpt from that country emissions screen. You see here then use of Voyager's navigator.pop to navigate back to the previous screen. Another Compose multi-platform library we're showing is this KMP port of Android's Material 3 window size class. This allows creating adaptive UIs based on a set of window size breakpoints that we can generally apply across the various clients. And this is an example of different layouts we dynamically showed depending on the screen size, showing list and details in a column on the left, and then showing in a row as this window is resized. And we see this in action here as well. These particular layout configurations are, of course, just one example, Another common approach is to switch between a list detail as the window gets smaller. And this is the distilled version of some of the code used. The specific layouts here aren't too important. The key thing here is that we're querying for the window size class and showing different layouts depending on what it's set to. And the UI will get recomposed then whenever a change causes the width or the height of the screen to cross a breakpoint. Okay, last thing, or well, it was the last thing, as we'll see a second. Second last thing, as it turns out now. Okay, last thing I'm going to show here, also from the Climate Trace project, is a small example of Compose UI code being consumed on iOS. We have, for example, this compose function in our iOS main code in our KMP module. It uses Compose Multiplatform's Compose UI view controller, which in turn includes a country list compose function, which is in shared compose code. And then on iOS, we take advantage of the ability to include a view controller in SwiftUI code. Here we define such a view controller, this UI view controller representable struct, and that in turn invokes the shared compose country list view controller we showed in the previous slide. Here we also pass a callback that's invoked when a country is selected in that list. And we're using this approach in several of the samples. And there is one more item, as it turned out. I got off the plane yesterday and saw that the latest Compose Multiplatform beta now had more complete support for Jetpack Navigation. Again, as Martin mentioned in his talk earlier today. So hacked some changes to the Climate Trace to try it out, available in a branch if people are interested to take a look. Very cool capability to have, and one more thing that will make migration from Android-only apps much easier. So that was a whirlwind tour of many of the Kotlin and Compose multi-platform libraries used in the KMP samples I'm involved in. Hopefully you got at least a flavor of the capability these libraries provide and how they can be used. As mentioned, I'll make the slides available, and they can be hopefully used or act as somewhat of a reference for folks that want to look into them in more detail later on. Merci beaucoup.